Good afternoon. Can you hear me? Technology class? Okay, so can we start? Okay. Good afternoon and welcome to lecture 6 of ECL 706. If you remember, in the last 3 lectures, we have covered formwork materials and some of their properties. We discussed timber, plywood, steel, aluminum and some other formwork materials. In today's lecture, we are going to discuss different issues pertaining to formwork design. So, we are going to see what are the various issues that needs to be considered while designing a formwork. Designing the formwork means we want to arrive at the suitable cross section of members, suitable members, so that it is able to resist the load which it is supposed to be exerted on, these formworks. It should be safe against overturning and many such issues. Before starting the design, there is one fundamental thing that you must understand. There is not much difference in formwork design when you compare it to the processes of permanent design.
Conference recorder playback service.
Okay, so if you just look at this particular slide, the first sentence, the opening sentence says that the formwork shall be designed to meet the requirements of the permanent structure using relevant standards for materials selected for formwork. So, as far as the design is considered, it should be similar to what you have been doing it for the design of permanent structures, not much difference. However, given the fact that you are going to put the formwork only for a limited period, sometimes the rigorous analysis may not be required. Sometimes the rigorous or the very exact calculations may not be required. But that does not mean that when it comes to a very complex kind of a formwork which is subjected to a very heavy load, you should be very careful, because sometimes poor design may result in even fatality of workers or the supervisors. So, as long as you are dealing with a typical structure, typical formwork, you can be little relaxed in your approach in such a manner that you are not going in for the very detailed calculation, you are not going in for the detailed analysis, but given the empirical data you have, given the empirical knowledge you have, you can utilize that and use those principles for designing your formwork. Now, there are certain requirements when you are trying to design a formwork. The important ones are the safety. Safety is paramount. Overturning. Sometimes you find that your loads are not evenly applied onto the formwork. So, sometimes I will show you one sketch. Through which it will be clear to you, or for that matter, I will tell you with the help of this sketch. Suppose you have one formwork to be constructed for, let us say, this slab, and you have erected these props, something like this. Now, when you, let us say, apply very heavy load, very large amount of concrete here, you may find that this support may get lifted up. So, your formwork must be safe against overturning also. It must be safe against overturning. So, the first parameter is safety. Your formwork must be safe. It should carry all the loads safely. Then you should also ensure the overall stability. You should also ensure the overall stability, and you should prevent any possibility of a collapse. Prevention of collapse is a must. So these are some of the prime requirement of any formwork design. It should be safe against overturning, it should be stable, and you should prevent all the possibilities of collapse. Because many a times you will find that poor design results in many of these consequences, such as there could be a collapse of your formwork, and then the whole concrete may be wasted, and sometimes it may even endanger your workers, supervisors. So any design, any formwork design must take care of all these 4 aspects. Now if you talk of a design process, formwork design process, as I told you, it is very much similar to what you do for permanent design, design of permanent structure. First step is obviously to estimate the load. This is obviously the prime requirement, estimate the load. The second requirement is form the design basis. Step 3, you can try to estimate the permissible stresses. Depending on what material you have chosen. For some of the material I have already given you the values of permissible stresses, both in bending as well as in direct compression and tension. And finally you analyze and design each component. Analyze and design each component of your formwork. So this is a 4-step process. First is to estimate the load, then form the design basis, estimate the permissible stresses depending on what material you have chosen, and then analyze and design each component. When you say analyze, depending on the importance of the structure, the analysis could be rigorous or it could be approximate. So this could be either approximate for regular structure, for regular formwork, whereas it would be very detailed. You can say detailed analysis or rigorous analysis for complicated formwork structures, and especially when the consequence of collapse is very high. That means it may result in fatality also or major injuries. So in such cases you should go in for detailed analysis, and then you should design each of these components. We will see what are the different components depending on the formwork type. But before that, I would like to tell you all these 4 steps one by one. So first we take up the estimate of load part. What are the loads coming onto your formwork? And in fact, before this, you must have certain information. Certain informations are needed before you proceed with all the following 4 steps. Certain informations are needed. We will see what are those information. For example, if you see, you should have the site investigation report. It would give you details of many things. For example, what kind of soil is there, what kind of foundation can be given, all such things. This anyway you have for permanent design, so that also can be consultant. You can try to identify what are the possible loads that are likely to act, because there are different loads which may not be relevant in all the situations. So we have to identify what are those loads. For example, for hilly region, this snow load could be a important load type, snow load, but in a place where there is no possibility of snow, you don't consider this, snow load or ice load, you don't consider this. In an area which is not earthquake prone, you don't consider earthquake load. So this is what I mean when I say that you try to identify which loads are likely to act on your formwork. So suppose you are working in an area where these loads are not likely to be there, then in such cases you don't have to consider those loads. You also try to find out the expected loading schemes, for example, how you are planning to construct your building, what structure you are likely to take it up first, and corresponding to that you will try to understand how the load flows, whether it's going in from column to whether it's going in for slab and beam to column and then to the footing. All such things you have to try to identify before trying to proceed with the design. Then in case of formwork, the sequence of erection and dismantling, these are very important. Sequence of erection and dismantling of formwork, these are very much required. So the knowledge of this, because if you are trying to follow a given sequence, the loads may act differently. The moment you change these erection and dismantling pattern, your loads are going to be different. Similarly, the sequence of concreting, in what sequence you are going to cast your concrete element, that also is of immense value to you. Sequence of concrete, how exactly you want to construct. As an example, I will tell you with the help of one sketch. Say you are wanting to construct a wall, like this. I am showing it in plan, right? Now suppose this length is maybe 15 meter length. Now you first identify, you made a sequence that okay, for first 3 meter I am going to fill it completely, and then maybe in a step manner you are going to cast it. So this may have slightly different loading values, because the pressure would be different, and that's why it's important to understand how you are planning to concrete it. Now what I am trying to say is, suppose this is in cross section, suppose that for first 3 meter you want to fill it up till here. For first 3 meter you want to fill it up here, maybe in half an hour. Now this will have a different pressure compared to a scheme in which you say that you are going to pour only, let's say, half of it, maybe only 1.5 meter in, let's say, half hour. So that's why I told you the sequence will impact your loading pattern. Is it clear to you, technology class? Do you understand it? Your mic is not switched on. Okay. Then as I told you, these are some of the information that you must need to explore before you proceed for estimation of loads. Now there are different types of load. You may have to estimate the dead load. So if you just see, you have dead load, you have imposed load, also known as live load some cases. Then you have environmental loads, and lateral pressure. It will come, we will discuss this separately. Lateral pressure exerted by concrete onto the formwork surface, and maybe some incidental loads, on account of maybe erection and dismantling. So these are the various loads that you may consider depending on the requirement. Now the same thing what I have showed you, I have put it in a diagram form. It is shown in the computer slide. If you just have a look at this particular computer slide, if you just have a look, it gives you the details of all the loads that we discussed. You can see we have categorized it mainly into three groups: dead load, imposed load, environmental load. Under dead load, you have again three categories: self weight of formwork, any ancillary temporary work connected or supported by formwork. Then you have weight of the freshly placed concrete. So this is these are some of the major dead load categories. Likewise, we will see imposed load also. Under imposed load, the major thing is the lateral pressure and the live load coming from construction personnel, plant and equipment, and then there are unsymmetrical placement of concrete, sometimes concentrated load. We will see each one of them in detail, and first we go through this dead load of formwork. And as you can see, it consists of three major categories. I will write it, the slide may not be that visible. So under dead load you have this self weight of formwork, this is first. Then any load which is supported by this formwork, any load supported by formwork, okay, and then you have the weight of concrete, weight of freshly placed concrete. These are the three examples of your dead load. Now ideally, if you look at the self weight of formwork and how do we find it, ideally you should be taking the individual weight of different formwork components in order to find out the self weight. But this exercise would be a little difficult. So these codes, standards, they give you some tentative value to start with. tentative values to start with, which can be cross checked later once you have finalized your design. So it's basically trial and error. So initially you assume, and then maybe later you can cross check once you have finalized all your formwork components. So if you talk of Indian standard IS, it says you can take 500 Newton per mm square, 500 Newton per mm square, rather 500 Newton per meter square, which is approximately 50 kg per meter square of load. So in normal situation you will find that the self weight of formwork is coming to be roughly about 50 to 60 kg, 50 to 60 kg. Now as you know, depending on what formwork you are using, these weights are likely to vary. For example, if I just have to make one sketch here, suppose you want to do this formwork. So you have some sheathing material, supporting material, and let's say these are supported on let's say some tripod as well as props. So if you are using maybe this system, the weight per square meter could be something else, whereas if you are using a tower system, that means this is supported on, let's say, some tower, something like this, its weight is going to be something different. So that's why I told you, depending on the system that you have chosen for your formwork, the self weight of formwork would vary. This is more heavier form, more heavy. This is a little lighter. But to start with, as I told you, you can take about 50 kg per square meter of self weight. Is that clear to you, technology class? Okay. Now coming to the second dead load category, it says any load supported by formwork. Now suppose on this formwork itself, you have certain brickwork. Now this brickwork load is also being absorbed by these formwork. So you have to consider the loads coming from such member also. So depending on what is the height, depending on what is the density, depending on what is the area in which this material is spread, you may have to consider it. Suppose I give you some material, let's say it's a brick, and you have, let's say, 1 meter by 1 meter brickwork of, let's say, 500 mm height. Let's say the density of the brick is 1800 kg per meter cube. Can you find out what would be the load? This 1 meter by 1 meter plan area brickwork is of 500 millimeter height. Height is 500 millimeter, length and breadth both are same, 1 meter, and density of the material is 1800 kg per meter cube. Can you tell me what would be the load coming onto it? It would be 1800 multiplied by 1 into 0.5. This is millimeter. So this would be 900 kg. 900 kg for how much area? 1 by 1, 1 meter by 1 meter. This is plan. So, your load is basically 900 kg per meter square. So, is this clear to you, technology class? Is it clear? Okay. Now, coming to this third category, load is also coming from the concrete that you have placed on the formwork, whether it is wall, whether it is column, whether it is beam and slab. So, whenever you are pouring the concrete, it also adds to the dead load. Now, in order to calculate that, you must have to find out the density of your concrete. If you are having a high density concrete, naturally its weight is going to be more, right? For normal concrete, unless it is something very unusual, you can assume this to be 26 kilonewton per meter cube. So, the weight of, or rather the density of fresh concrete, you can assume it to be 26 kilonewton per cubic meter for formwork purpose, for formwork design purpose, right. So, if you have to calculate the weight of, let us say this is your slab and beam, right. This is 300, this is 500, this is also similar, and let us say you have this as 3 meter, right, 3 meter, and slab thickness is, let us say 100, let us say it is 200, slab thickness is 200, right. So, for the slab portion, can you find out the dead load coming from this particular thing? What is the load coming here, this portion, on per square meter basis? Can you tell me? For the slab portion, what is the load? This is the slab portion I am talking. What is the load per square meter? If the thickness of the slab is 200 millimeter. Yes, anybody can tell me? See, how do you calculate the dead load in case of a permanent design of slab? What you do? You consider 1 meter strip. So, you take 1 meter strip and its thickness already you know 0.2, right. So, how much would be the weight per square meter? 26 is the density, 26 multiplied by 1 multiplied by 0.2, which is 5.2 kilonewton per square meter. Is that clear to you? Okay. So, this is going to be 26 multiplied by 1 into 0.2, which is 5.2 kilonewton per meter square. So, this is the load from the fresh concrete. Okay. Now, we move on to the so we have considered 3 types of dead loads now, 3 types of dead loads, in which first one we discussed was self weight of formwork. Normally, you can take about 500 Newton per meter square. Then any temporary work, if it is getting supported on formwork, then you will take the actual load and then put it in your calculation. Finally, the weight of freshly placed concrete, including reinforcement we are talking, is 26 kilonewton per cubic meter for your formwork design consideration. Now, we move on to the imposed load part. Now, the imposed load basically has 4 main types of loads. The first one is the lateral pressure. The first one is the lateral pressure. We will spend more time on this because for permanent structure design you may not have been exposed to this aspect. This is typical to a formwork design, very commonly used in case of formwork design. Now, in order to understand the lateral pressure, I will give you two examples of pressure. Let us say if you have water, suppose you have a container in which you have put some water, let us say up to this height, this is filled with water, right, and let us say there is the same container, you have filled it up with some solid, full solid. This is liquid, this is solid. Now, when it comes to pressure exerted on this surface, you know it would be something like this. At the bottom you have the maximum pressure, at the bottom you have the maximum pressure. If the height of this liquid is h and density of this is gamma, so your pressure is gamma into h. When h is 0 here, we are measuring h like this, 0 here, h here. So, when h is 0, this is 0 here. So, this is typical of a liquid. In case of solid, you will find that the pressure is 0 throughout. So, this is 0. Now, when it comes to concrete, what you have done is, now you have put fresh concrete into this, let us say into this container. How its pressure would be, that is what we are interested in finding. Whether this would be like this, whether it should be 0 throughout, what exactly is the shape, what exactly is the pressure, magnitude of pressure at different heights. This is what we are interested in finding. You will find that concrete behaves neither like a true liquid nor like a true solid. It is somewhere in between. Right? It is somewhere in between. Now, many researchers, they try to develop certain theories which can explain the magnitude of pressure at different heights. Now, you do not find any exact theory which explains the magnitude of pressure at different heights. So, we have to rely on various experimental results that has been conducted over a period of time in order to understand the pressure distribution along the form height. Now, different agencies have conducted research and they have suggested some expressions for calculating these lateral pressures. So, we are going to discuss all those important codal provisions. We are going to understand all those empirical equations, tables which would enable us to calculate the lateral pressure in different cases. Now, when I say empirical, I have to explain you how in what sense they are empirical. What they do is, suppose they want to calculate the pressure at different heights of the column. So, let us say they make a sample in which, let us say, the column height is, let us say, 2 meter or maybe even 3 meter. Let us say this is 3 meter. They took a given type of cement. They measured workability, the slump. They measured the temperature at the time of placing. Likewise, they measured various parameters. In fact, they kept some of the parameters constant, and then they put these pressure gauges at different heights, maybe here, maybe here, maybe here, maybe here. So, these are your pressure measuring devices installed. Remember, there are no theory. So, they would try to get a large number of experiments done, and then they will try to physically record the pressure. Now, they pour the concrete here and they will measure the pressure here. So, they have sufficient data through which they can find out what is the pressure here, what is the pressure here, what is the pressure here, what is the pressure here. So, they plotted this. Now, they did this experiment over a large period, under different varying conditions. Sometimes they change the slump, sometimes they change the temperature, sometimes they change the cement, sometimes they change other parameters, sometimes they change the method of compaction. Whatever parameter they thought that would have an impact on lateral pressure, they conducted experiments using all those parameters. Okay, and based on those experimental results, they tried to fit certain equation. It is like this. Suppose you have two sets of data, x and y. You have two sets of data here, corresponding to each x you have different y's, right? Now, you can try to plot this. Let us say you have x axis, you have y axis. You try to plot these points on this xy plane. So, now you have got all this. Now, you try to find the best fit line, maybe somewhere here, and you try to find its equation. So, this is what exactly they tried to do. Now, remember, they do not have an equation like this, y is equal to 5x plus 6. If you are given this equation, you can find out the value of y for any given value of x. But here the xy values are known to you and they are not following any given pattern. So, you are trying to find the best fit line. So, they are trying to find the best fit line. So, all those data they collected, they tried to plot it, and then they tried to develop certain equations. Now, using these equations, they are able to find pressure under different temperature condition, different rate of rise, different workability conditions, different cement type, and that is what we are going to learn now. What are those different formulas? What are those different tables? What are those different equations? This is what we are going to learn, right? But is the process clear to you? How did they arrive these equations? How did they arrive these tables, which we will soon be seeing them? Is that process clear to you? Their approach, how did they find out why they did it in this manner? Is that clear to you? Clear? Okay. So, in this lateral pressure thing, we first study this formula given by this Construction Industry Research and Information Association. Construction industry, this is known as Syria. It's a UK based firm, construction industry. They conducted lots of experiments, and based on their findings, they have suggested certain formulas as well as certain tables, and which are most widely used for formwork design, especially for computing the lateral pressure. So, this is Construction Industry Research and Information Association. Right. Now, they have given a formula for maximum lateral pressure, which is slightly complicated. You know why? Because there are so many variables involved. D multiplied by C1 under root of R, I will tell you what this R means, minus C2 K under root of H minus C1 under root R. First, you note down this formula. P max is D multiplied by C1 under root R minus C2 multiplied by another constant K under root of H minus C1 under root R. So, at any height, whatever is the maximum pressure, you will be able to calculate it using this formula. Now, I will explain you what are these different terms. P max is maximum lateral pressure, and its unit is kilonewton per meter square. Now, one thing you must be understanding, whenever you are using these empirical formulas, it is very essential for you to use the same unit which has been recommended. So, when they ask that you are going to get this in kilonewton per meter square, so whatever result you are getting, that is in kilonewton per meter square. When it comes to D, D is the weight density of or you can simply say density of concrete, and its unit is kilonewton per meter cube. Its unit is kilonewton per meter cube. Right. Now, C1 and C2 are constants. C1 and C2. C1 depends on size and shape of formwork. C1 depends on size and shape of formwork. C2 depends on material of concrete. especially the type of cement that has been used to prepare the concrete. So, C1 depends on size and shape, C2 depends on material of concrete. They have also specified different values for C1 and C2 depending on what material we are using for concrete and what kind of size and shape of formwork are in use, right. H is the vertical form height, this is in meter, this is in meter. Then you have this capital R, which is representing the rate of pour, or you can say rate of rise of concrete, let us say, and this is in meter per hour. This is in meter per hour. T is okay, before T I will tell you K. K is basically temperature coefficient. K is temperature coefficient. This is given by an expression called K is equal to 36 divided by T plus 16 whole square. 36 upon T plus 16 whole square. Now, T here is the temperature at placing, concrete temperature at placing, and its unit is degree Celsius. Now, many of these terms you already know. For example, the density of concrete you already know. C1 and C2 I will give you the values. H is the vertical form height, whatever height you have chosen to make form, that is your capital H. R is the rate of rise of concrete. R is the rate of rise of concrete. I will tell you how this is calculated, rate of rise of concrete. Suppose you have a wall of 300 millimeter width, this is of 10 meter length and its height is 3 meter. If its height is 3 meter, suppose the total concreting time is 1.5 hour. Can you find out what would be the rate of rise? R is what? Just try this very simple question. You have a 10 meter wall, 300 millimeter thickness of 3 meter height, which you have planned to concrete it in 1.5 hour. What is the rate of rise in meter per hour? Rate of rise you have to calculate in meter per hour, because this is how your expression has been evaluated. Can you find it out, please? All of you are getting 2? We will try to find. First I calculate the volume. Volume is 10 meter by 3 meter by 0.3 meter. So, this is this much cubic meter. So, this is 30 into 0.3. So, it is 9 cubic meter. All of you have got this volume? Is it all right? Okay, 9 cubic meter, you are doing it in 1.5 hours. So, how much is this? This is 6 meter cube per hour. This is, that means every hour you are pouring 6 cubic meter. But remember, you want it in meter per hour. Now, 6 meter cube hour has 3 meter height. So, R is becoming 6 divided by how much? 3, which is 2 meter per hour. So, all of you are getting this? Okay. So, this is how you have to ensure the correct unit. Remember, in empirical formula, it is very essential to stick to the unit that has been specified in the formula. Now, I will give you the values of C1, which is dependent on size and shape of the formwork, and C2, which is basically dependent on the constituent material of concrete. So, just try to see the C1. This table gives you the value of C2, and just a minute. Okay, first you write for C2. So, can you read this or should I write it?
Hello, Professor.
Yes, please.
Just we are not clear with the calculation.
Okay, you are not clear with the calculation. I will do it once again. Okay, let's go back to this particular piece of paper. Volume, you are clear till here? Volume? Volume of concrete, you can find it out clearly?
Yes, it is clear.
Okay. Is this clear? 9 cubic meter, I told you that you are completing it in 1.5 hour.
Yes.
So, this must be clear to you?
Yes, that is clear also.
Okay. Now, I will make one sketch. This is the cross section of wall. This is 300 mm and this is 3 meter. Okay. Now, this wall you are pouring at a speed of 6 meter cube per hour. Okay.
Okay.
Okay. Now, height is 3 meter. So, every hour, how much height you are filling it up? Is it clear to you now?
There is some confusion still.
Let's say this is 1 meter, 2 meter, 3 meter. Okay. Every hour you are doing 6 cubic meter. So, 6 cubic meter per hour means 3 meter will be filled up. So, you are interested in how many meters you are filling it up in 1 hour. Not clear? Okay, just let me see if I have another slide in which I have another example. Okay, just a minute. Sorry, 6 cubic meter per hour. What we can do is, it is, let's say 3 meter, you are filling it up in 1.5 hour. So, how much is this? This way also you can do it. Is it clear? Now, let's say I am doing it in a simple way. 3 meter you are
Simple formula.
is this clear?
Yes, in this way it's clear, but in your previous way that's not clear.
Okay, now follow it like this. You have 3 meter height, you are filling it up in 1.5 hour. Okay, so every hour how much? It's 2. Either you do it that way or this way. If you are understanding it, it's fine. Now is it clear to you?
Yes.
So can we move ahead now? Okay, what you can see is I have one more problem. I have one more example. Now you just do it. Just look at this. Find the lateral pressure. Okay, I will not show you this slide because it contains answer also. So just see this, 15 meter by 3 meter by 0.2 meter. This is your wall. And now let's say rate of pour is, I am giving you directly, rate of pour is 10 cubic meter per hour. Okay, can you find out R? Now this we are doing it in a slightly different manner. I have not given you the time. I have given you the rate of pour itself, but in different unit. Can you find it out? R. R, you know, it has to be in meter per hour. So, are you able to find it? How much is that? Pardon me? I am not getting you. Answer is 3.3. That's right. Okay. How we do it is like this. You can calculate the volume. How much is this? 9 cubic meter. Right? 9 cubic meter. So, how much time you will consume? The total time would then become 9 is your quantity and you are pouring at a rate of 10 meter cube per hour. So, this much hour. So, 0.9 hour is the time that you have to take to fill it up. Now, 0.9 hour for how much height? 3 meter. 0.9 hour for 3 meter. So, what is the speed? 3 divided by 3 is the height divided by 0.9 hour. So, this is how much? This is what 3.3 you have got. Three by 0.9 is 3.3. Is it correct? Okay. So, now you have any doubt? In first case I gave you the time. Here you are supposed to find the time based on the rate of pour, which is given in meter cube per hour, but now you understand how to calculate this R value. Now, going back to those coefficients, I will just write it for you. Just give me 1 minute. Okay, this is how C2 is defined. C2 for OPC, RHPC or SRPC without admixture. Without admixture, this is given as 0.3. Similarly, OPC, RHPC or SRPC with admixture except retarder. This value is also 0.3. Now, OPC, RHPC or SRPC with retarder, it is 0.45. The value of C2 is 0.45. Okay. Fine. These are the suggested values of C2. Now, some more cases are there for which the values are given. This is LHPBC. I will tell you what are these term standing for: PBFC, PPFAC or blends containing less than 70% GGBFS or 40% PFA with admixture. For this also you have C2 value as 0.45, right? Sorry, this is without admixture. Now, same thing, LHPBC, PBFC, PPFAC or blends containing less than 70% GGBFS or 40% PFA with admixture. In the previous case it was without admixture, here it is with admixture, except retarder, and for this it is 0.45 again, except retarder, it is 0.45. Then there are two more cases, I will show you after you read this, after you complete this. Okay. So, I will just give you the two more values, which is LH, PBC, PBFC, PPFAC or blends containing less than 70% GGBFS or 40% PFA without with a retarder. For this C2 is 0.6, and finally blends containing more than 70% GGBFS or 40% PFA. For this also it is 0.6. So, I have given you the values of C2 corresponding to 7 cases, and depending on the situation you can use these values, which are mainly 0.3, 0.45 and 0.6. So, this is as far as C2 is concerned. Now, when it comes to C1, C1 is 1 for wall and it is 1.5 for columns. 1.5 for columns. So, if you are using the expression for the computation of lateral pressure on wall, you can use C1 is equal to 1. When it comes to column, you can take it as 1.5. Now, have you written this? 1 for wall and 1.5 for column. So, C1 and C2 both are now known to you. Now, whatever terminologies I have used, you can just note it from this particular computer slide. For example, OPC stands for ordinary Portland cement. Most of you must be knowing this. LHPBC is low heat Portland blast furnace cement. PVFC is Portland blast furnace cement. RHPC is rapid hardening Portland cement. PPFAC is Portland pulverized fuel ash cement. SRPC is sulfate resisting Portland cement. GGBFS is ground granulated blast furnace slag cement, and finally PFA is pulverized fuel ash. So, now you remember that C1 is depending on the shape and size of your form, whereas C2 is dependent on the constituent material for concrete. So, depending on what blend you have used, depending on what cement you have used, the values change from 0.3 to 0.6, 0.3 to 0.6, whereas C1 varies from 1 to 1.5 depending on whether you are doing it for wall pressure computation or whether you are trying to calculate the column pressure computation. Now, you might have noticed that the expression given by the Syria is slightly complicated. So, people may not be liking to use that, they may not be inclined to use that. So, in order to help the designer, what they have done is they have developed certain tables. For different parameters. So, depending on what parameter you are using, you can refer to these tables and you can calculate it. You can calculate the lateral pressure depending on your concrete element. For example, you might have noticed that you are using this these expression primarily for wall and column. So, you have two sets of table, one is for wall, another is for column. Now, in wall and column both, corresponding to C2 is equal to 0.3, corresponding to C2 is equal to 0.45 and corresponding to C2 is equal to 0.6, you will get expression. Now, depending on the temperature, depending on the R value, and depending on the form height H. So, for different values of these parameters, they have made certain tables. Similarly, for column also, for different C2, 0.3, 0.45 and 0.6, and different temperature R value and H value, they have prepared certain tables. So, I will just show you some sample tables. What you can do tonight is you can try to cross check these values by actually using that formula. You can develop it in Excel spreadsheet also, and then you can actually try to cross check the table which I am going to show now. So, if you just look at this particular slide, this gives you the design formwork pressure for column. So, whenever you are trying to design a column, you can refer to these tables. Now, one of the parameters is form height, and then you have concrete temperature. This table shows for two temperature values, for 10 degrees Celsius and for 15 degrees Celsius. The rate of rise I have varied from 0.5 to maximum of 3. In between values I have taken as 1 meter, 2 meter. You can have different rate of rise according to your design, and accordingly these values will change. So, suppose I tell you to find out the pressure for column, and if you want to use a form height of, let us say, 3 meter, form height 3 meter, R value of 2.0 meter. Okay. This is what we got. Concrete temperature, let us say it is 10 degree, or let us say 15 degrees Celsius, right, and let us say it is OPC, RHPC, cement, okay, without admixture. Suppose this is the condition, and I have to find out the maximum pressure. Remember, we are trying to calculate maximum pressure, P max. This is what we are interested in finding. So, you will just have to look at the relevant table for column, Now, using this table, can you tell me what would be the pressure? H is 3, R is 2, temperature is 15 degrees Celsius, and this table is valid for the two categories, OPC, RHPC or SRPC without admixture, and OPC, RHPC or SRPC with any admixture except a retarder. So, this table is valid for these set of constituent materials for concrete. Can you tell me the values by looking at this particular slide? Rate of rise 3 meter, concrete temperature 15, and rate of rise is 2 meter and form height is 3. So, any idea how much is this? Can you just read it out? 65 kilonewton per meter square. So, this is what we have got it from the table. If you want to use those formulas, you can do that, and then you can cross check this value. Is it clear? Now, any value that is not given in table, you can interpolate, you can extrapolate, or else the best would be to use the formula itself directly. So, likewise I have given for different values of different design formwork pressure table for columns. You can see this is for concrete temperature 20 and 25. Now, this is for different concrete groups. As I told you, there would be 7 sets of material, and for this you have a different table. This table is valid for concrete temperature 10 and 15, and for what concrete groups they are mentioned in this slide. Similarly, you have for other 20 and 25 degree Celsius temperature. Likewise, for different other concrete groups you have these tables. I will send you these tables, do not worry. Now, for the walls, you see here also, depending on the rate of rise, depending on the form height and concrete temperature, you can generate tables or else use the formula. So, is it clear to you, technology class? Okay. So, whatever we have discussed in this particular lecture, I just want to summarize. We have started a new topic, formwork design, wherein we are discussing different issues which are of interest for formwork design. The basic philosophy of formwork design is similar to that of any permanent structure design. However, depending on the situation, we sometimes may not like to do the detailed analysis. However, for complicated cases of formwork or where the consequences of collapse are very high, we use rigorous analysis followed by the detailed design. The requirement of formwork is that it should be safe. First of all, it should be stable. All possibility of collapse should be prevented. There are different steps involved in formwork design. For example, right from starting with estimate of loads to forming the design basis, finding out the permissible stresses, and followed by the analysis and design. In this class, we have discussed the first part, which is the estimating the load, and that too we have just been able to cover the dead load and one part of imposed load. Under dead load, you have self weight of concrete, which you can take it as 500 Newton per millimeter square, Newton per meter square, roughly 50 kg per meter square. Any load that is being supported by formwork, you have to take into consideration. Self weight of concrete including reinforcement, you can take it as 26 kilonewton per meter cube, right. Then we moved on to the imposed load. There we discussed the lateral pressure. Lateral pressure computation, as you know, these are based on experiments, and so there are empirical formulas. One of the empirical formulas that was given by Syria, we have discussed in detail. You know, in the expression you have the coefficients C1 and C2. C1 is 1 for wall and 1.5 for columns, right. 1 for wall and 1.5 for columns. C2, depending on the constraint of your concrete, it may vary anything from 0.3 to 0.6. Rate of rise, you know how to calculate in meter per hour. K, you know how to calculate. I have given you the expression. Sometimes you may like to use tables, so they have also given you these tables depending on whether you want to compute the lateral pressure for wall or column, right. These tables you can interpolate, extrapolate for intermediate values and values which are not listed out in the tables, or the easiest thing would be to use the expression, right. So, one of the tasks that you have to perform today is to check these values of table vis-a-vis what is given in the, what you get out of the formula. In the next class, we are going to learn another method to calculate the lateral pressure, which is given by American Concrete Institute, ACI. We will also see how in Indian standard lateral pressure is calculated. We will also see the German code, the DIN standards, and then we will see some other topics relevant to formwork design. So, if you have any doubt, please feel free to ask. Thank you. Thank you and good night. Okay, what about the questionnaire survey? Did you send it to them? Where is my friend Kelkias? When will you give? Some more? Okay, you have sent. Okay, whoever has not sent, please help him, because sometimes you may also be in this position when you take up some dissertation works. So, if you have done good work here, somebody will also be helping you. Okay. So, thank you and good night.